Good morning. Today I will continue the subject of my previous lecture about first billion years of our universe, starting from cosmological recombination up to cosmological reionization, simply reionization, which is at redshift between 8 and 6. After cosmological recombination, we have unically adiabatically baryonic gas with well established theoretically physical condition, number density of particles, chemical composition, temperature, dependent temperature on cosmological redshift, and so on. But we have very poor observational information about this epoch, about formation of the first stars and galaxies, which doesn't exist in this epoch. They started to form in this epoch from initial density and velocity perturbations generated in the very early universe in inflation epoch, quantum fluctuation of space-time matrix. So in our this epoch is important to our study, because this epoch is important for our understanding how the first object, the first stars, first galaxies are formed in the medium with primordial chemical composition, where hydrogen consists about 90% and the rest is helium without practically other elements. And we hope to obtain answers for very important questions about first galaxies and maybe about nature of dark components of other universe, and maybe also another, for example, primordial magnetic fields. So, in previous lecture, I showed that most abundant element, hydrogen, has unique physical properties. Its ground state energy level of hydrogen atom has hyperfine structure splitting caused by spin flip of electron with spin of proton, nucleus of atom, and fin split results into emitting of line with 21 centimeter in rest frame, or 1420 megahertz frequency. Integration of radiation transfer equation give us expression for differential brightness temperature, which is proportional to intensity in this line on the backlight of cosmic microwave background. And we show that this is a small distortion of cosmic microwave background, but it is practically accessible for observation. Such differential brightness temperature depends on cosmological parameters such as density of matter, which consists of baryonic and dark matter, especially depends on density and energy density of mass density of baryonic component, its ionization state, its perturbation, and also on temperature of cosmic microwave background and spin temperature, which reflect the excitation state of hyperfine structure level. I show in previous lecture spectral features in the redshifted hyperfine 21 centimeter light. We show that sense temperature of baryonic matter at the redshift lower than 500 is a bit lower than temperature of cosmic microwave background as backlight, because dark ages medium of dark ages, intergalactic medium of dark ages, result in absorption light at redshift about with maximum absolute value at redshift 80, where collisions, effect of collisions between which excite hyperfine line is maximum. At lower redshift, other effect is very important. Rotational field effect with appear when the light of the first sources appear. Ultraviolet radiation with Lyman alpha photons influence population of excited and ground-based level of hydrogen over level of hyperfine structure of second energy level. And here is shown how this absorption light depend on X-ray radiation, which ionize the medium, and Lyman alpha one photons, which caused the Rotational field effect. So this in this range absorption detection of absorption light can say us about the formation of first sources of ultraviolet soft and hard ultraviolet radiation caused by first sources, population 3 or population 2, or maybe shock waves or formation of first supermassive black hole or other physical phenomena which can result in the radiation in this electromagnetic spectrum, range of spectrum. Up to now, we have only one announcement about detection, absorption light in the range between in the redshift range between 10 and 20, which was announced by a team of experiments to detect global epoch of reionization signature, published in Nature in 1918. But this year, other experiment, SARAS 3, shaded antenna measurement of the background radio spectrum, shows that maybe edges result is incorrect. Maybe the result which was presented as signal from dark edges has instrumental origin, and confidence level of closeness of this discovery is enough high. We must wait on the new experiment, which will say us who is correct. Experiment edges or experiment SARAS. I hope that SARAS also detect in this range signal, but with I suppose a 10 or more times lower than announced by HST. We also show that perturbations which are in this epoch causes the perturbations in the intensity of 21 centimeter hydrogen line, and can estimate evolution of amplitude of the power spectrum. This evolution in redshift reflect the spectral features which we shown in previous slides, and much have such dependence of scale. Most accessible for observation is scale about 0.1 and larger, and the predicted amplitude is compatible with current upper limits. We also estimate in the signal in other way. We can compute signal from separate halo, which are warm. The baryonic method in halo, each warm or maybe hot, depend on many processes which are during mineralization of halos. And such a halo will be source for emitting radiation emission. It will be a source of emission 21 centimeter in 21 centimeter line, and we can estimate the beam average antenna temperature in 21 centimeter, and here is shown how such beam average antenna temperature depend on redshift for halos of different mass. And here is parameter close to the experimental technique for comparison. And the values for the range of mass of Hertz, for two range of mass of halos are shown for different redshift, and here is corresponding 21 centimeter frequency, line frequencies which depend on the redshift. And here is for this range of mass of halos, and here is for essentially wider diapason with lower minimal mass. This range approximately corresponds to cold dark matter, and this one of warm dark matter, model of dark matter. So we see that maximum is for emission in cold dark matter about 100 or 200 microkelvin, and it is in agreement with observational limits obtained up to now in Murchison wide field array and LOFAR European radio telescope of light. Now we have also cosmological simulation with hydrodynamical and radiative transfer in 21 centimeter line to estimate evolution of some patch of the sky. Here is cube with 0.5 megaparsec side, and evolution from redshift 13 to redshift 20 and redshift 10 for three sources: halos only, intergalactic gas only, and intergalactic gas and halos. At large redshift, we have only absorption, as we see, very scale, first and middle row, top and middle row is in linear scale of differential temperature, and last is in log. And here we see very bright halos, which is can be visible in emission. So, in 21 centimeter line of atomic hydrogen is can be very important signal, and it will be informative about physical conditions in dark ages and cosmic dawn before realization. From current semi-analytical computing, we can state that at a larger redshift, the important mechanism for excitation this line is inelastic collisions between neutral atoms of hydrogen, and which is dominant in comparison with other. And this mechanism pulls the spin temperature to the kinetic one in the dark ages intergalactic medium. The absorption or emission line of 21 centimeter atomic hydrogen, which is due to Scheiben field effect, the position of this absorption line profile and depth are sensitive to the first light model of cosmic dawn, and therefore to the scenario of formation of the first-time galaxies. The absorption line depth of 21 centimeter at 78 MHz found from Edge's experiment is far out of the prediction of the standard cosmological model with post-Planck parameters. The predicted global 21 centimeter signal of hydrogen is in the range of 50 to 150 microcarats and is accessible for detection by Hawking radio telescope. The development of theoretical method for modeling the formation of the absorption emission line of 21 centimeter atomic hydrogen during the dark ages and cosmic dawn and their detection are important and promising tasks of modern cosmology. But the next question is, are they possible to observe at higher frequencies where foreground is not so large? The 21 centimeter is informative, but they are in the range of in dark edges, dozen megahertz, where foreground is very large. Foreground caused by synchrotron of our galaxy as atmosphere, as radio interferometric signal caused by our phone, radio station, and so on, in technological processes. And the best place for observation in redshifted 21 centimeter line is far side of Moon. Such experiment are planned in the next decade. But even in this place, we cannot remove galactic synchrotron. The value is about 4,000 in temperature Kelvin, and the frequencies between 50 megahertz. The first absorption features are in the frequency about 20 megahertz, where foreground is larger. Because observation or some signal in higher frequency are preferred. What can be there? We return to chemical composition of periodic medium in dark ages and cosmic dawn, which follow from primordial nucleosynthesis and kinetics of chemical reactions, which is known and we can then compute and predict chemical composition. And we know that in this epoch are first molecules such as hydrogen molecule, deuterium hydride, and helium hydride, iron molecules, and we expect that the rotational, vibrational levels of these molecules can be excited by in collisions and radiation, by radiation, which is in this epoch there are cosmic microwave background and in cosmic dawn the light of the first source. So we estimate the level of such radiation and possibility to observe them by existing state. Here is energy structure of hydrogen molecule, hydrogen and helium hydride ion, and normalized energy distribution of cosmic microwave background and different redshift is shown, and also for comparison the energy distribution of Planckian radiation with temperature 1000, 10,000 kelvins, and we see well at which energy level can be excited by the radiation. So we can expect that some intensity in this line can be possible, and we can estimate the level of radiation. For such estimation, we suppose that during first billion year of our universe, in the decade of our universe, in dark ages and cosmic dawn epoch, we have cosmic microwave background with known temperature, which is described by a Planck function. And also we have radiation of first light, also caused by Planck function with some temperature which depend on redshift, and some parameter which define the energy density of such radiation. And we will constrain this parameter by those observations which we have now. We have observational data about a range of radionization. In these figures, we show energy distribution of cosmic microwave background, cosmic infrared background by green line. Cosmic microwave background is shown for three redshift 8, 6, and O, which we observe now. And the energy distribution at epoch of reionization also is shown by red and blue line, and we call it them as first light or light of first sources. Solid light is for reionization at redshift 8, and dashed line for reionization at redshift 6. Dotted line is the same radiation that if it exists at current epoch. So it is lower than cosmic microwave background. The amplitude or energy density of such of this spectral energy distribution is in agree with epoch of reionization. The dilution factor alpha is constrained by this data. By vertical dashed line is show the vertical dashed line show the potential of ionization of hydrogen atom and photodissociation of molecules, and lowest is for negative hydrogen atom ion, H minus. Each radiative rate can be presented for such model of radiation in simple form and can be used for estimation. There is data which I showed in previous lecture, which show us where reionization place. It is between 8 and 6. This data follow from low polarization of cosmic microwave background given by Planck collaboration, and also from observation of Van Patterson's rule in spectra of high redshift quasars and lemon break galaxies. Here is shown dependence of hydrogen fraction, ionized hydrogen, hydrogen fraction, dependence on redshift, and we see how between redshift 8 and 6 reionization of hydrogen caused by first light is to understand how energy density of first light depends on temperature, taking into account information about redshift of reionization, is shown dependence of dilution factor of first light described by a Planck function on temperature of first light epoch of the reionization. In the temperature when the first source appeared from collapsed cloud, in the collapsed cloud, the spectral is changed, and it can be described as increasing the temperature, increasing the number density or energy density of such radiation. And in our model, it is taken into account by dependence of temperature of first source on redshift. And here we see that dependence of dilution factor on temperature is very strong, but do not strongly depend on rate of change of temperature of first source. And here is range. For this value, lower value is for ionization at redshift 6, larger for redshift 8, and we see that value is not, difference is not large, but the difference is large for temperature. It can mean that fluctuations of radiation is very large in the cosmic dawn epoch, because different regions are at different distance from the source, of course. And in one place place we have hot, or a source with hot ultraviolet, and other with soft ultraviolet, and we will have a large fluctuation of this signal. So, to estimate the intensity in the molecular lines, we must estimate how many such molecules are in dark edges and cosmic dawn epoch, and we must take into account a lot of reaction. Here is presented only name from them. The rate for each reaction is taken from different sources. The complete list of the sources is in this paper. Here is kinetic equation which describes formation, destroy, and destruction of molecules caused by collisions between molecules, which results in formation or contra, which destroys them with C minus. And last term is caused with radiation, photodissociation of molecules. This equation must be completed by cosmological equation, dependence, expansion of the universe, by Hubble factor, dependence of baryonic matter and dark matter on redshift, and also of energy balance. We discussed that in previous lecture. And results for intergalactic medium for number density of particles from cosmological recombination up to ionization is shown in top part of this feature for baryonic, for helium, and for deuterium atoms. In the bottom feature by green line is shown the temperature, evolution of temperature of cosmic microwave background. Solid dark line cosmic of dependence of baryonic matter temperature. Color line solid and dash evolution of temperature of first sources, and we before realization after at lower than 10 redshift, we see how this first light hit the baryonic matter. For such toy models, we can estimate how depend the number density of first molecules on redshift before, during cosmic dawn, and after and before total ionization. It is shown by color lines, blue for ionization by hot light and first light, and red blue for reionization at redshift 8 and red for reionization at redshift 6. Left column for warm fast light and or soft soft radiation, and right for radiation fast light with 10,000 Kelvin. And we see that difference is consists that when energy density of fast light becomes some level, molecules are the number densities of molecule decreases because effect of photodissociation of molecules. But another situation is for iron molecular heavy iron. For some models, for example, fast light with larger temperature, but essential lower number density, contrary, the number density of this ion increases because importance of this reaction. When first light ions have enough energy density, the number density which ionize the hydrogen, a larger number density of proton result into formation of iron helium hydride ion. And other model we see, for other model we will see, we will also essential difference in the number density. So we can conclude that fluctuation of fast light will result into fluctuation of number density of fast molecules in cosmic dome before reionization. It is useful to compare the number density of molecules, fast molecules during cosmic dawn with first light and without first light. And here is shown the ratio. The ratio number density of molecules which is shown by different color: black hydrogen, hydride deuterium blue, and helium hydride ion red. In all the two number densities, the same molecules without fast light. So figures show how fast light and which for different models, how it influences the number density. We see that number density of hydrogen molecule and hydrogen deuterium molecules break down when number density of energy density of fast light become essential. And we see that situation is the same. Dotted line for radiation which reionizes medium baryonic matter at redshift 6 and solid at redshift 8. So this molecule disappear before reionization. But molecules of helium-hydrogen ions, helium-hydrogen ions has different behavior depending on model of the first light, and we see that in some from them this ion molecular number density increases during cosmic dawn epoch and survive during reionization. It is important because maybe it is impossible, we find possible to observe some flows in the line of these molecules. You know that a few years ago this molecule was detected in planetary nebula. And it is important now, which is signal in the lines of first molecules, which level is it possible to detect them. We may estimate them. You'll mention that observable frequency of each transition between different energy levels depend on redshift, where these molecules emit the photon in corresponding energy transition. Frequency is decreased in factor 1 plus z, and wave length is redshifted in factor 1 plus z. To estimate the intensity in the light, or differential intensity in the light of cosmic microwave background, we solve the kinetic equation for population of the molecular rotational levels. We estimate the rotational level here. The rate of reaction include excitation, de-excitation include spontaneous transition, induction, collision, and absorption, and deactivation by collision. And we can estimate the global signal as from all sky. And here is results of integration of radiation transfer equation along width of line at fixed redshift. When we integrate them for each line, it is shown in the right column. This expression gives possibility to estimate the differential intensity in the line for different transition, which is shown by different color. Solid line show the total intensity caused by all line at fixed frequency. When we integrate over a redshift this value, we obtain signal in the frequency, dependence on frequency. Here is spectral radiance, in Jansky per stereo. For standard model, where standard practically lambda CDM model, and we see that at frequency about from a few dozens up to a few hundreds gigahertz, we have the absorption in the caused by first molecules. But if we see here the values times -4 and times -3 is very small. It is such absorption or such spectral features as absorption in this frequencies is too small. The same is for other molecules. Deuterium and helium hydride plus. Moreover, the value here is too low, essentially low. So it looks that the spectral features of first molecules are, but the amplitude is maybe too low to observe by the current technique. As illustration, I show also what will be if we have non-standard lambda CDM model or standard lambda CDM model with primordial magnetic field, which can dissipate, decay, heat the baryonic medium, and in this case we can estimate the line profile, and we see that in this case we have emission, and very large emission. But we have not enough good data about primordial magnetic field from the other observation, which are Planck data. We have upper limit about 3 nanogauss, but is other data which suppose that such field must exist to explain the lack of Gauss photons from blazars which emit TIV photons. The lack Gauss photon can be explained by existence by intergalactic primordial magnetic field in void and intergalactic medium, and we have a lower limit for such magnetic field. And this figure, only for illustration, is presented that molecular lines is sensitive for such physics of the early universe. Especially the interesting is profile, spectral features of the line of molecules, hydride ion, but amplitude is low. In comparison with other, which is the signal in comparison with another one. In the left figure it is shown the foregrounds which we know. It is spinning dust, thermal dust, free radiation of our galaxy, synchrotron, and cosmic infrared in the background. In the right column is shown from previous features, spectral features of hydrogen molecules for primordial magnetic field 3 nanogauss in comparison with other expected or predicted signals which distort the cosmic microwave background. And now is planned a few experiments to detect different distortion of cosmic microwave background, such as Virus, Voyage, and other. And here is Sunyaev-Zeldovich distortion is shown here, and some sensitivity of experiments which is planned for Voyage is level of sensitivity and virus. So we see that molecular sensitivity of first molecular lines to the primordial magnetic field, but it is comparable with other, but at the upper limit, which is permitted by Planck data. Now we try to estimate the emission of first halos in the line of first molecules, because we return from discussion about microphysics, and return to cosmology, and before to discuss the emission line from separate or single halos, we discuss how to prepare such halo from initial perturbation. Formation of elements of large-scale structure, galaxy, cluster of a galaxy, or void, are described well by gravitation instability theory, which was founded by Lifshitz in 1946. Lifshitz is archaeophysicist at the beginning, the last after the Second World War. He was productive physics of which work in the Moscow Institute. According to this theory, we describe the evolution of density and velocity perturbation with its scalar perturbation in the space-time metric, and present them as in connection with metric perturbations. Here is equivalent of nu is equivalent to as gravitational, classical gravitation potential. we can present local density as some deviation from averaged and fixed time. This value is called as density perturbations. The velocity, local perpendicular velocity, form velocity can be presented through string velocity. In such ways, there is four components for velocity, and tensor energy momentum tensor can be presented in general case as density perturbation of each component and velocity, and also if component has pressure, we will have corresponding pressure background value plus perturbed one. And the cosmological background, of course, gravitational potential and all density and velocity perturbations are zero. Here is Friedman equations from which describe the expansion of the universe in cosmological models with radiation, matter, and dark energy in the general case. Einstein equations we used and energy momentum and energy momentum conservation law to equations which describe evolution of gravitational potential, density and velocity perturbations of each component. It is quite a linear equation which can be solved for using available integrator. We will use pressure formalism for description of the last stage of formation of halos. Before we analyze the evolution of spherical perturbation with top hat profile, it is enough for estimation, because metric is presented in spherical coordinates, and we suppose that each values depend on time, perturbed values, and radial coordinate. In case of spherical symmetric equations are simplified, and only scale of spherical top hat perturbation are presented as key wave vector from initial perturbation is left here. We analyze evolution of perturbation in a four-component medium, which consists from radiation, dark matter, dark energy, and baryon component. We analyze them in hydrodynamical approximation, for which we need to have equation of state, which is known for radiation component, for dark matter, which is collision velocity, can present equation of state parameters, which describes the pressure as W times C2 square and mass density of each component. And for dark matter it is zero, because it is collisional value. For dark energy it is free value, and we suppose it as function of redshift or constant. In the simplest model of dark energy, we suppose that it is a constant value. And for baryons, equation of state is known, and we can approximate its values which depend on state of ionization and temperature. Also, the square of sound is known for radiation, 0 for dark matter, because it's collision with, for dark energy, we suppose equal 1, that is correct for dark energy as scalar field. And for baryonic component, we suppose also known effective sound speed. Initial condition for such perturbation we take from the observation from Planck plus HST plus Wigler Z plus supernova away, which give possibility to determine the amplitude and spectral index of the initial power spectrum of curvature perturbation. In the linear regime, we can present we can obtain simply relation between amplitude in each component, dark energy, dark matter, baryonic and radiation component in the very early universe, in the conformal Newtonian change. With such cosmological initial conditions, we can integrate the equations which describe the evolution of each component, and here is presented in the top part of each feature the density perturbation of each component, solid dark lines, dark matter, blue dotted line, baryonic component, green line for relativistic component, which is radiation and neutrino, and dark dashed line is dark energy. It is dynamical dark energy, not cosmological constant. For cosmological constant, we have not, of course, any perturbations. In the bottom, the same for the same component is peculiar velocity, and here is instead redshift is value as scale factor from matrix, and relation between redshift and scale factor is very simple. Each from us can compute them. For A equal 1, correspond to current epoch, we have zeros for redshift. And for A, when A go to 0 at the beginning of the universe, we have Z infinity. We start from A 10 to minus 8. It means that we start from redshift 10 to 8 in very early universe, and in the such change, we see that in all component the density is independent on redshift. It is correct. And in the left column, we have evolution of each component for one model of dark energy, and in the right column for another. They differ by values of effective sound speed of dark energy. In the left one, it is usual color film as typical model of dark energy. In the right, in the feature in the right column, is dark energy with very small effective sound speed. And we see that such dark energy can collapse together with halos, dark matter halos, in halos. Now we can estimate for such, we can compute the evolution of other values up to visualization, for which we use Paris-Schechter formalism, and obtain the number, density, and temperature of each component. We analyze two models of halos. That line describes evolution of temperature as result of adiabatic cooling and adiabatic heating during collapse formation of hot halo. And red line is with temperature which follow from virial serialization, when difference between potential and energy difference between potential at time around point up and after realization, this energy is transferred into heat of baryonic component, and we can estimate this temperature in such way which depend on mass of the halos and redshift at which this halos is realized. Yet we can estimate the mass for fixed mass of halo and initial amplitude, which we put close to Rootman square values, and estimate for such halos redshift of virialization, temperature, density of dark matter, number density of hydrogen, deuterium and helium atoms, molecules, and we can compute, of course, chemical composition, evolution of chemical composition, and in halos, physical parameters of halos in the radius and angular size in the sky in arcsecond. Here is presented the mass function for such halos at different redshift, from redshift 80 up to redshift 10. Dark line for lambda CDM model and dashed red lines for lambda VDM model, VDM warm dark model for two model of lambda VDM model with free streaming scales at mass 10 to 5. Sorry. 10 to 5 and 10 to 7. 10 to 7. Here is a result of estimation how chemical composition evolve in such halos. Solid line is shown for halos in which the temperature evolve according to adiabatic heating, and dotted line with it is called halos with regularized temperature. And we see the molecules of hydrogen molecules and hydrogen molecules increase after formation of halos, but iron molecular helium deuterate plus contrary in case of large hot halos decreases because collision destruction of molecular is important. Here is shown the ratio of molecules with and without fast light for warm solid line and hot halos. And we see that the situation is similar. The fast light destroyed the molecules, hydrogen molecules and HD molecules, but evolution of H plus molecular is different. We can estimate now the emission, that the temperature of halo is larger than the temperature of cosmic microwave background. We expect that the halos will can be observed in emission of in rotational vibrational line. To estimate intensity, we compute solve the kinetic equations. For spherical halos, we compute vertical depths, differential brightness temperature or intensity. It is exact solution of transfer equation for spherical homogeneous top hat halos, and here is differential temperature averaged over projection of the sphere on the sky, and the result is for intensity of one main line plus molecule is shown here in this slide for ro halos in the light of first molecules, and we see that first two molecules disappear. Both model of first light helium H plus molecular contrary, which can be brighter before reionization. Reionization is at 6 or 8. And here is for different model 3, 4 columns for different models of first light. So we will have very large fluctuations which depend on place in the sky. What we have is observation. Up to now we have only, I know, only one experiment which gives a upper limit signal in the frequency of first frequencies of first molecules, and it was obtained by Odin satellite, Swedish, in 2010 years. We see that upper limit peak intensity is in the range, essentially higher existing estimation of the signal. Is it possible to observe the light in by other telescopes? Yes, in this range, Planck telescope give 9 maps. Here is one from them, and maybe signals from halos, maybe hot halos are in this map, but the amplitude, as we saw, is about tens and more times lower than the amplitude of cosmic microwave background fluctuation. Maximum values, which is here, is about 10 to minus 7. But it is not very pessimistically. I hope in the nearest future the next generation telescopes like Planck will be accessible to observe signals of at such level, and maybe we obtain very important information about cosmic dawn and dark ages, baryonic medium, where the first objects are formed. Also, other telescopes are available to observe in this range. It is ALMA, and in the few years the scale will start to work, and it will also can observe this epoch. So the conclusions too are as follows: that the thermal radiation of the first sources with temperature from 4,000 to 12,000 and more, and dilution coefficient in this range reunites the interhalo medium at between redshift 6 and 8. The higher is temperature, the lower is energy density of the first light. Such light destroys the hydrogen and hydrogen deuterium molecules, H2 and HD, in the direct photodissociation reaction before the ionization. The molecule of helium hydride, helium H plus, survives until ionization due to association reaction, which results into formation of this molecule. But if the dilution of first light is not exceed 10 to minus 10. The warm halos are brightest in the line of 2000 gigahertz of helium H plus molecules. At this level of differential brightness temperatures, and at this frequency of molecular HD. And hot halos are brightest in the light of hydrogen deuterium molecules. We see that amplitude is enough maybe for telescopes of next generation and maybe existence. Thank you.